Let me go through Chapter P, Day 1 notes. So first off, this is all going to be review, but finding intercepts, the way we find x and y intercepts. To find x intercepts, what we do is we take the equation, we find the y values, we set y equal to 0, and then once we have that, then we solve for x. And if the equation has both numerator and denominator, then we only solve for x in the numerator. So we basically ignore the denominator once we replace y with 0. To find y-intercepts, we're going to set x equal to 0, and then we solve for y. So x-intercepts is going to be where the graph crosses the x-axis, and then y-intercepts is where the graph is going to cross the y-axis. Okay. Next, determining symmetry algebraically. If we want to determine whether the graph has y-axis symmetry, algebraically what we do is take all your x values and then replace them with a negative x. And if the negative x goes away, then we know that our equation will have y-axis symmetry because the equation remains unchanged. So basically this will happen whenever you have x being squared, because a negative x will just revert it back to a positive x. And an example of y-axis symmetry is a parabola. If we have y is equal to x squared minus 1, for instance, we see that there is y-axis symmetry. We can take this graph, we can fold this along, fold the graph along the y-axis, and we see that the graph is going to overlap each other. X-axis symmetry, what we do is we replace all the y values with a negative y, and see if the equation remains unchanged. If it does remain unchanged, then we know that the graph has x-axis symmetry, meaning that our equation or our graph will overlap nicely over the x-axis. So instance of that will be x equals y squared plus 1, where we have the graph symmetrical about the x-axis. Okay. Origin symmetry is where if we can replace the x and y values with negative x and negative y respectively, and if the equation remained unchanged, then we know we have origin symmetry. An example of this will be y equals x cubed, okay, where if we take an ordered pair and if we replace this with x and negative x, it's still going to remain as a point on the graph. Okay, so the question that we can ask based off of these three graphs is, can the graph with x-axis symmetry be functions? So if we look at something that has x-axis symmetry, like this middle graph here, we see that this cannot be a function because it's not going to pass the vertical line test. For each and every input, there can only be exactly one output, and we see that there is two of the same y values for a given x value, so we know that anything with x-axis symmetry cannot be a function. Okay, so example 1, describe the symmetry of the following: y equals x squared. If we replace this x with a negative x, we're going to get back to x squared because the negative x will just go away, and we know that's going to be a y-axis symmetry. Y equals x cubed. If I replace y with negative y, if I replace x with negative x, the negatives will remain, but then we'll cancel out from both sides, leaving us with the original equation. So y equals x cubed will give us origin symmetry. Y equals x squared minus x. If I replace x with negative x, I'm going to get x squared plus x, and that's not going to give us the same as the original equation, so there is neither y-axis, x-axis, or origin. And finally, x squared plus y squared equals 25. If I replace x with negative x, the graph will remain unchanged. If I replace y with negative y, it'll go back to the same. If I replace both x and y with negative x and negative y, it'll go back to be the same. So this graph has all three: x-axis, y-axis, and origin symmetry. And the reason why is we have a circle that is centered around 0, 0. So no matter how you fold the graph or you flip it or turn it, the graph will remain symmetrical for all these three types. All right, finding points of intersection. Right, the way we do this is we solve an equation for one variable, and then we substitute it into the other equation. So let's look at example 2. Find the points of intersection for the following. We have x squared plus y squared equals 25. This is a circle centered around 0, 0 with a radius of 5. And we have a linear equation, 2x plus y is equal to 10. And if we just think about how circles and lines can interact with each other, we can kind of decide what are some possibilities for points of intersection, or how many solutions we're going to be getting. So if we have a circle and if we have a line, it's possible for the line to intersect the circle at 2 separate points. So we could be expecting 2 ordered pairs, or 2 points of intersection. But it's also possible that the line is tangent to the circle, meaning that the line will only touch the circle at one point. And if that were the case, then there's only going to be one intersection and therefore only one solution. So we know that going into this problem, we're going to be expecting either 2 ordered pairs or 1 ordered pair, depending on how the line and the circle are oriented with each other. Okay. So we're going to follow the steps by trying to solve the equation for one variable. So we're going to try to get it down to one variable, and then once we solve for that variable, then we can substitute into the other and find the ordered pairs. So we have a circle, we have a line. I'm going to try and get one variable by itself, and the easiest variable that I'm going to that will be to solve will be for y. So I'm going to solve for y. Y is equal to negative 2x plus 10. And then once I solve for one variable, I'm going to substitute this back into the other equation so I can get this circle equation down to just one variable. So negative 2x plus 10, I'm going to replace that in for the y variable. Okay, so when I have that, I'm going to get x squared plus negative 2x plus 10 quantity squared equals 25. And I can expand this binomial to become 4x squared minus 40x plus 100. And then now when I'm down to this, I'm going to bring everything over to one side of the equation so that I can pull out GCF as well as to factor. So once I have everything on one side of the equation, combine some like terms, 5x squared, subtract the 25, I get 75. So once I have this, I can factor out the 5, and I'm left with trinomial that I can factor. So x squared minus 8x plus 15 factors down to be x minus 5 times x minus 3. Solve for x, I get 5 and 3. So here we know that the line is going to intersect the circle at 2 separate points. Okay, so now we're going to plug into the other equation so that we can find the ordered pairs. I'm going to plug 5 and 3 into the linear equation so I can solve for y. So when I plug 5 in for x, I'll get negative 10 plus 10, which is 0. When I plug 3 in for x into the linear equation, I'll get negative 2 times 3 is negative 6, plus 10 is 4. So then my ordered pairs will simply be 5, 0, and 3, 4. Okay. All right, going back to something that we covered at the beginning of this video, is finding x and y intercepts and discussing symmetry. So I'm going to go through an example here. That will discuss symmetry, and we're going to determine that algebraically. So x equals y squared plus 1, we're going to find the x and y intercepts for this and also decide whether there's any symmetry with this graph. And to recall x-intercepts, we simply set y equal to 0. To find y-intercept, replace x with 0. So first I'm going to try and find x-intercepts. So replace y with 0. I'll get 0 squared plus 1, so x equals 1. So therefore my x-intercept is simply 1, 0. To find y-intercept, I'm going to replace x with 0. So x gets replaced with 0. 0 equals y squared plus 1. Y squared equals negative 1. Now, we're not going to get a real number if we take the square root of both sides. Square root of negative 1 is imaginary, so therefore there's no real number. There's no y-intercept. The graph is never going to cross the y-axis. Okay. To determine the symmetry easily, what we can do is we can just simply identify the order, the variable that has the squared, because Any variable that has a squared, we know that when we replace that variable with a negative, it's going to go back to a positive. So I'm going to guess that this probably has x-axis symmetry. So I'm going to replace y with negative y. Negative y squared goes back to y squared. So this reverts back to the original equation, remains unchanged. Therefore, we know that this graph has x-axis symmetry. And the way we did that was we knew that the equation remained unchanged when we replaced the y with a negative y.